Good day. Today we're doing lesson 5-7, and you may have had a different bell ringer warm-up. I'll just run through this one briefly with you. Remember, when you're watching the videos here, you need to pause when I present a problem so that you have time to work it, then start the presentation back up so that you can see the solution. If you just watch it straight through and don't give yourself time to think about things or take notes, you are not doing what you need to as far as being an interactive learner with this presentation. So if you didn't do a warm-up or you need a little brush up on the things that you see on the screen, do this bell ringer. Now the solutions. On the first one, by angle measures, that would be an acute triangle. The second is a right triangle. When you multiply on number 3, we haven't done a whole lot with the square roots. You'll get a 12. Now how do we get that? It is 2 square roots of 3 times another 2 square roots of 3. Everything's just multiplied together there. So let's just rearrange and group together what we can. 2 times 2 is 4. Square root times square root is square root of 9. Square root of 9 is 3. Oops, not an equals. So 4 times 3 is how we get the 12. And the last solution should be 49x squared, because that was 7x times another 7x. Again, you can rearrange if you need to. 49x squared. Today's lesson is working with the Pythagorean theorem and doing it in the converse way. And we will be working with some square roots and some binomials. So I have some problems for you to practice some skills that we did earlier in our class or in Algebra 2. So time to shut this off and do the simplifying and squaring and then check to see if you did it right. For the simplifying radicals, you should have 5 times the square root of 3, 6 times the square root of 2. The binomials, squared, and simplified would be those. If you got those right, you can fast forward this a little bit, but if you need the explanation, here's how you worked them out. Square root of 75. 75 is 3 times 25, and that's 5 times 5. So square root of 3 times 5 times 5, we're looking for pairs. So that pair comes out, and then the 3 is still in the radical because it doesn't have a duplicate factor to go with it. 72, maybe you did 2 times 36, 6 times 6, 2 times 3, 2 times 3. So that would be square root of 2, 2, 2, 3, 3. There's a pair of 2's, so a 2 comes out. There's a pair of 3's, so the 3 comes out. And then there's a 2 left under the radical. So the 2 times 3 is where we get the 6 times the square root of 3. Okay, squaring your binomials. Okay, this is not distributing. You cannot just take that exponent and put it on both parts. So what we have when we square it, we have x plus 2 times another x plus 2. This was called distributing or FOIL. So you can't distribute the exponent, you distribute the whole expression. So x times x was x squared. X times 2 is positive 2x. Now 2 times x is another positive 2x. And 2 times 2 is 4. You should have 4 terms when you multiply 2 terms times 2 terms. Now these middle 2 terms often combine. And so that's where in the answer I got x squared plus 4x plus 4. The second one, or the last one, x minus 5 times x minus 5 Again, FOIL or distribute together. X squared minus 5x minus another 5x. And negative times negative is positive, so that's where we get the plus 25. Combine like terms, x squared minus 10x plus 25. All right, those are some skills that we will use in our lesson today. So let's try not to make the mistakes. Okay, our objectives today, we're going to use the Pythagorean theorem and its converse to solve problems. Use the Pythagorean inequalities to classify triangles, what type of triangle it is. So we will also describe what a Pythagorean triple is. A refresher on the Pythagorean theorem. As it says, it's probably the most famous mathematical relationship. In chapter 1, we reviewed it, and a lot of you knew what it was. You have to have a right triangle in order to use the Pythagorean theorem. It says that the sum of the squares of the lengths of the legs, which we call A and B, equals the sum of the square, or equals the square of the length of the hypotenuse. And C in the picture is the hypotenuse. So leg squared plus leg squared equals hypotenuse squared. So as we run through a few practice problems from the Pythagorean theorem, a difference I want you to do on the problems now is we're not going to go to decimal. Notice the directions say put your answer in simple radical form. So do the reducing of radicals that we refreshed and learned about in order to simplify. As you set up each problem, pay attention to which is the hypotenuse and which are the legs. All right, do the problem. Now to check your answer, the 2 and the 6 were both the legs, and so the x was the hypotenuse. 4 plus 36 was 40. Square root, technically there's a positive and a negative when you do the square root as you're solving. I'm ignoring the negative because when we're working with lengths on figures, measurements are not negative. Now simplifying the radical, after I did the factoring tree, the 4 would be 2 times 2, so the 2 comes out and the 10 stays in. Next problem. Pause. Okay, the difference on this problem is that you are not finding the hypotenuse, you are finding the length of one of the legs. So your variable would be one of the legs, so a squared plus 15 squared equals 20 squared. Square each value, subtract, square root, ignoring the negative, and let's see, I had the square root of 175, so how did I get to that answer? 175 would be how many quarters? That would be 7. So I have a pair of 5s and an extra 7, so that's how the answer 5 times the square root of 7 was done. Okay, this one has still the right triangle, but now we're introducing some algebra expressions. So here's where we will need to do that squaring of a binomial. Which side's the hypotenuse? It's the x plus 4. So putting it into the Pythagorean theorem. And we just need to square out correctly. I'll be careful on that x plus 4 squared. Do that as we did on the bell ringer. I'll do it off to the side. X plus 4 times another x plus 4. X squared plus 4x plus another 4x plus 16. And these will combine. So when I show it, it's going to be x squared plus 8x plus 16. Now combine like terms, so let's get all the x squareds on one side. I would subtract x squared from each side. notice what happens. X squared is going to subtract out on the left and on the right. So you no longer have those variables. I'd probably subtract 16 from each side so that I can get all the numbers on the left and all the variables on the right. Now divide. We get x to be 16. If you need to, be sure you pause it so you can finish those notes. Okay, try this one. Notice that you do have variables on two things. Pay attention to which are the legs, which are the hypotenuse. Go ahead and pause me. Okay, as you come back, here's our solution. When you square that x minus 2, you get x squared minus 4x plus 4. Then add that 16 more onto it. Okay, what happened to my x squareds? As I was simplifying, I subtracted x squared from each side. Now I'm going to bring one of those terms over. I just chose to make the positive come over and then divide. So if you wanted to check those sides to really see what they are, to see if that made sense, if x is 5, that means the hypotenuse is 5, this leg's 4, and this leg would be 3. So the sides are 3, 4, and 5 on that triangle. Here's a story type problem that uses ratios. You'll see that 3-to-1 ratio in the description. Okay, read through what's here. So it might help to draw a picture. It says that we have a rectangular picture frame. Go ahead and put this in your notes. On a rectangle, I think you know enough about a rectangle to know opposite sides are the same. We'll get to that chapter. We want the length to width to be 3-to-1. Okay, 3-to-1 means the length is going to be 3 times as long as the width. So we're going to use that to set up our unknown sides. The diagonal is supposed to be 12. Okay, so in my picture, here's the diagonal. That is 12. The length is supposed to be 3 times the width. I don't know what the width is. And the width, I'm going to use the shorter direction. I think in my solution I called it x. And then the length would be 3 times as much. So I'll be using x and 3x as the legs of a right triangle. If I get rid of part of the picture, do you see the right triangle? So this is just simply another Pythagorean theorem problem. We have to do our calculations correct. I think my picture is going to disappear, so make sure you write it down if you haven't got it yet. Directions do say round to the nearest tenth, so we don't need to worry about radicals in this problem. So here's where I'm clarifying that I'm using x and 3x. I'm using that because the ratio 3-to-1 just means that the length is always 3 times bigger. It could be 3 and 1, it could be 6 and 2, it could be 12 and 4. So just multiplying with that variable keeps the relationship 3-to-1, but makes it a larger number or a smaller number depending what x is. Okay, so on the picture, realize the 12 was the hypotenuse, the x and the 3x are the legs. Why do I have the parentheses around the 3x? It's because I need to square the whole thing. If I don't have the parentheses there, it's only the x that's getting squared and not the 3. So my parentheses have to be there so that I multiply it right. Where did I get that? Well, when I multiplied the 3x and squared it, that's 9x. Plus 1 more x, or sorry, 9x squared plus 1 more x squared. That's where I'm getting the 10x squared. Okay, divide each side by 10. That's really going to be 14.4. Then you need to square root. We're finding a length again, so I'm ignoring the negative. So if you're doing this on your calculator with a decimal, this is like the square root of 14.4. We are going to a decimal answer because of what the directions said. See, the square root of 16 would be 4. Square root of 14.4 is a little bit smaller, so 3.8 should make sense. Okay, next problem. Again, pause this so you have time to work. I'll discuss a little bit. Find the value of x. Answer in simple radical form. Notice we've got two right triangles. Is the great big triangle a right triangle? It is not. There's no right angle marked there. And I don't really know what that x length is, so I cannot really justify it any other way. So how are we going to find the value of x? This is a two-step problem. If I look at the triangle that x is on, just the x, there is a right triangle there, but I really only know one length, the 11. So it's hard to find, or actually impossible, to find any missing side of that triangle when I'm missing two sides. So let's look at the right-hand triangle, or the left hand. I'll highlight it in blue. Okay, on that triangle, I have 3 for a leg. I'll put A for the other leg, and square root of 34 for the hypotenuse. We can do the Pythagorean theorem on that triangle to figure out what A is. Then we'll have two numbers for the right-hand triangle, and we can do the Pythagorean theorem again. Pause and try it. Okay, if you're back, 3 squared plus A squared equals square root of 34 squared. 3 squared is 9. Square root of 34, when you square it, square root of 34 times square root of 34 comes out to be just a plain 34. The squaring and the square rooting will cancel each other out. Try it on a calculator if you don't have that. Okay, subtract 9 from each side. A squared is 25. Square root using only the positive value for the length, so A is 5. Now let's switch to the red triangle and again do Pythagorean theorem. X squared plus 5 squared equals 11 squared. (121 minus 25). That would be 96. And the directions here say radical form. So can't go decimal. Divide your 96 down. Okay, did you divide maybe by 4? I'm going to go up where I have some room off to the side here. Whoops. 96. I went 4 times 24, 2 times 2, 2 times 12, 2 times 6, 2 times 3. So it looks like I have a lot of 2s. Okay, let me organize this a little bit. 1, 2, 3, 4, 5 2s. And a 3. So pairs, another pair. The 2 and the 3 don't simplify because there's no pairing. So I'm coming up with 4 times the square root of 6 for the value of x. Take some time to look through that and think through it again before you move on. All right, this one is almost the same look. Well, it has the same look to it, but I am asking you something different. This says find the perimeter and the area and give your answer in simple radical form. You're going to have to go through, very similar to what we did on the last one, to find that perpendicular height and then to find that hypotenuse. Then we can find the perimeter and the area. So you do have to find some missing things. So pause this, calculate both of those, and then start me back up. Okay, as far as what you should have found, this should have been 4 because you were doing 3 squared plus a squared equals 5 squared. Okay. Then switch to the right-hand triangle. And I think this one comes out radical. So let's see what I get. 4 squared plus 6 squared equals x squared. 16 and 36 makes, I think, 52. And then square root. Factoring, I think we can take a 4 out. 2, 2. So it looks like I have a pair of 2's and a 13. So this side is 2 times the square root of 13. Okay, now let's find the perimeter and the area. Okay, perimeter is simply add up all the sides. So for the perimeter, I need to add 5, 2 square roots of 13, and 3 plus 6, that's 9 for the bottom. So I'm getting 14 plus 2 times the square root of 13. You cannot add that together in radical form unless they both have the same radicals. So that's what it's going to look like for the perimeter. Area. What shape is this? It's a triangle. Triangle area, we reviewed that in chapter 1. 1/2 base times height. The base could be any side of the triangle, but then the height has to be perpendicular to it. So looking at what we have, the 4 is going to be the height, and the 3 and 6 together will be 9 for the base. So 1/2 of 9 times 4, half of 36 is 18. I did not give you any units to label on that problem. Okay, again, pause it if you need to think through that some more. And hopefully my answers came out right. Did I multiply right on that area one? 9 times 4 was 36, half of that was 18. Did I put 16? If so, my bad. Okay, Pythagorean triples. Okay, definition. It's a set of 3 non-zero whole numbers called a, b, and c, such that the equation a squared plus b squared does equal c squared. In other words, they work in that equation, and they don't have any decimals. They're whole numbers. That's called a Pythagorean triple. So numbers 3, 4, 5, those 3 are a Pythagorean triple because 3 squared plus 4 squared does equal 5 squared. Checking that out, 9 plus 16 is 25. If you try 5, 12, 13, they will work in the equation. 8, 15, 17, 7, 24, 25. If you know Pythagorean triples, it can help you solve right triangles easier. So if we would go back to some problems, I think there was one where I showed you 3, 4, 5 were the sides. That happened to be a Pythagorean triple on that triangle. Just some special numbers that always form right triangles. Okay, so back to finding the missing side lengths on some right triangles. Now the added directions here say tell if the side lengths form a Pythagorean triple and explain. So first, find the missing side length. Pause. Okay, the missing side length was 50. Okay, so now is it a Pythagorean triple? The side lengths are 14, 48, and 50. They are all non-zero whole numbers or integers. So yes, that makes a Pythagorean triple. Find the missing side. Pay attention to where the hypotenuse is. The missing side comes out to be 8 times the square root of 2. Right, is that a whole number? If you're not sure, try the square root of 128 and just go to decimal. Notice it's not a whole number or integer. So this would not be a Pythagorean triple because 8 times the square root of 2 is not a whole number. They all three have to be whole numbers. Find the missing side. The missing side was simplified to 2 times the square root of 41. So again, not a Pythagorean triple. One, 2.4, find the missing side. You might already know the answer to the second question. Looks like I didn't even find the missing side. I just answered the second question. Okay, what's the missing side? Let's see, 2.4 squared plus 1 squared. .76 square rooted. I get 2.6 for the missing side. So to make sure I did everything in the directions. Missing side 2.6. The answer is it still is not a Pythagorean triple. Find the missing side. And this one is 34. So yes, we have a Pythagorean triple. This wasn't in the list that I gave you, but was there 8, 15, 17? I think there was. Notice that 8 times 2, 15 times 2, and 17 times 2 is this Pythagorean triple. If you have one Pythagorean triple, you can multiply each by the same value and it creates another Pythagorean triple. Now let's talk about the converse. Converse means we're switching the order of the information. So where the Pythagorean theorem needed a right triangle to begin, this will have a conclusion that there's a right triangle. So this is part of how we will know what kind of a triangle it is. I think you might need to write the words down, the hypothesis, conclusion, so I think you need to pause me. Okay, coming back, it says if the sum of the squares of the lengths of 2 sides of a triangle is equal to the square of the length of the third side, then the triangle is a right triangle. So your hypothesis is the equation, a squared plus b squared equals c squared. If that is a true equation with certain lengths, then your conclusion is that you have a right triangle. Sometimes it doesn't come out equal. Often it does not come out equal. So if the c squared is bigger, what that does is that possible hypotenuse length got longer than what it would have been if there was a right angle. So that causes this angle to get wider, creating an obtuse triangle. If the c length is shorter, comes in, that's going to make this angle C get smaller. So something smaller than a right angle would be acute, and then all the angles are acute. So if the c squared is bigger than a squared plus b squared, it's obtuse. If the c squared is smaller, it makes a smaller angle, so it's an acute triangle. If you say it in that way in terms of the c squared, I think obtuse and big, acute and small would make sense. Here's a little bit more explanation of what I was trying to draw out there briefly. By the triangle inequality theorem, remember we said the sum of any two sides has to be greater than the third side. Otherwise, it's not going to make a triangle. So some of these, we won't even have a triangle being formed. Tell if the measures can be the side lengths of a triangle, and if so, classify the triangle, acute, obtuse, or right. If we have 5, 7, and 10, add together 5 plus 7. Is that bigger than 10? Okay, is 5 plus 10 bigger than 7? And is 7 plus 10 bigger than 5? All of those work, so yes, it will make a triangle. Now what kind? How do you know which to use for the A, B, and C when you try this classifying part? The C is always the possible hypotenuse, so it's always the longest length. So the 10 is going to be the C. The other two, it really doesn't matter which you put where. I'm going to compare it to C squared. So 25 plus 49, 74. 10 squared is 100. The 10 squared is bigger. So that will be an obtuse triangle. Now if I would put my less than or greater than symbol in there, you might get confused because I wrote that out by habit as a squared plus b squared equals c squared idea. In the notes, it was reversed. So I didn't want to put that up there to make it confusing. Here's what I had written out. Notice when I wrote it out, I put it on the left side. So still obtuse. The c squared is big. All right, will these make a triangle? And if so, what kind? Pause so that you can try it. 2 steps. Okay, as you tried to determine, did you notice that 5 and 8 is only 13? Those aren't going to reach and close to make a triangle. So that's not even going to make a triangle. You could skip the second part because there's no triangle formed. How about 7, 12, and 16? It does make a triangle. And the c squared is bigger, so it's an obtuse triangle. How about 11, 18, and 34? Again, pause so you can work it through. Starting back up, not going to make a triangle. 11 and 18 aren't long enough to close. So no second step because there's no triangle. Decimal lengths. Yeah, it's not going to be a Pythagorean triple at all because of the decimals, but we can still try to see what kind of a triangle. All right, when you added any two, it was always more than the other. So it does make a triangle. Classifying it. This time the c squared is smaller. So that's an acute type of triangle. Okay, time for you to test yourself to see if you got those figured out correctly. So pause and then see what the answers were. This first one, make sure you square out that hypotenuse correctly. Should get x to be 12. Second one, it might help to draw yourself a picture. It doesn't really clarify, but rectangular entertainment center. Okay, so we're trying the Pythagorean theorem. So how did I get that solution? I actually did 52 squared plus 40 squared. And I compared that to 60 squared. This work probably did not need to show a square root. So comparing, the c squared was bigger. Actually, what I'm saying might not be the way that you want to do that. You actually might just do, if it's a right triangle, figure out what the hypotenuse would be doing the Pythagorean theorem. Make sure that it's bigger than 60. I think that's more of what my work shows there. Now we have a just straight Pythagorean theorem, and then figure out if it's a triple. You might have recognized that from the list. 5, 12, 13 is going to be the hypotenuse.
Sorry for the interruption.
And the last one there.
To clarify questions about attendance at district competitions.
All right, I'm going to shut this off since they're giving announcements.
Competitions for any activities are not considered an excused absence. Only students or